So, the peak 18F instructions. So, as I was telling that there are 77 assembly language instructions in peak. Earlier peak versions they are 32 to 35 instructions, and then this instruction set, most of the instructions are 16-bit word length, and there are 4 instructions that are 32-bit long. So, that way those instructions are more powerful, but otherwise the instructions are uniform. So, they are 16-bit wide, but only 4 instructions they are 32-bit wide. If you look into these instructions, then the first category of instruction is the copy instruction or move instruction. So, this is move copy 8-bit number into W register. So, the format is like move LW 8-bit. So, move literal. So, it is like move literal to W register 8-bit number. So, this is some sort of move immediate. So, the coding will be like this, that 00001110, and then this is the 8-bit number that we have. Okay. Then another interesting instruction may be that copy contents of W register into port C. So, this is so for moving to some moving the content of this W register onto some memory location. So, move WF. Okay. So, this is working register port C comma A. So, this so it will go to port C, and here the A will indicate that the port C is in the current access bank. So, that is the current bank selection, whatever is there. So, it will be there, it will be used for that, and 82 hex is the port C address. So, this is the 82 hex. So, it will be useful there, and rest of the bits are fixed for this operation. We will try to see one very simple program. So, we will try to write a few instructions to light up alternate LEDs at port C. Okay. So, in the hardware connection, so we will have this port C, and is a bidirectional port, input and it can be configured as input or output. So, we have to set it for output mode for display, and then also logic 1 will turn on an LED. So, that is the structure. So, for this we will try to write the program. So, this is the structure. So, from the 8-bit data bus it will come to port C, and we have got this registers register and then the LED. So, if you put a 1 here, so the corresponding LED will glow, and there is a tri-state latch enable signal. The TRISC is a special register. So, if you want to enable port C, so you have to enable this latch, then only the values will be going to output. So, actually this port C has to be configured as either input or output. So, for that purpose this TRISC, so this has to be controlled. So, for the software side, first we write logic 0 to TRISC register for configuring port C as an output port, okay, and then we will move 55 hex to alternate LEDs. So, how do we do this? So, move LW 00. So, W register will be loaded with the immediate word 0, and then move WF TRISC. So, this will set port C as output port, okay. And now, after that I can put the byte 55 hex onto port C. So, just like 8051 for output we did not need to configure it, but whenever we are trying to configure it as input. So, we had to write a 0 first onto the write a 1 to the port first. So, that the latch was getting disabled. So, here also similar thing, that port C, the port C is a bidirectional port as we see here. So, for programming it is in output mode. So, you should have this TRISC latch set to so that we can get this this latch is will configure this port C in the output mode. So, if you send a 0 to TRISC, then it will set up the output port C as output mode. If you send it as all 1, then it will be configuring it as input mode. Then we are outputting this 55 hex. So, that is for the alternating LEDs will be on, alternate LEDs will be on, and then this pattern. So, this is moved on to the W register. So, you cannot put this pattern directly onto port C. So, you have to put it onto W register and then move WF port C. So, this will turn on the LEDs because this 55 hex will go to port C and it will be turned on, and then it will go to this sleep. So, that is the power down mode. So, it will so it is assumed that it will be after turning it on. So, it is going to power down mode. So, if you want that they should blink, then you should put a delay here and then do a shifting of this W register from 55 hex, it should come to the status AA hex, and that way you can put a loop around this. So, that you can get alternate blinking of LEDs. That is not shown in this program. So, for an embedded application, you see that this is going to be useful, because we have got this microprocessor unit, program memory and data registers. So, that are there. Then we have got this AD converters are there. So, AD converter we has got analog 0 channel. So, like this is a typical example, like we have connected one temperature sensor, one heater, fan and one LCD panel. Okay. So, it may be connected like this, that this temperature sensor will sense one analog value. Okay. So, that is that is connected to the AD converter, and for that connection we need to use this RA0 pin of this port A. So, port A I am connecting it in the input mode, and this temperature sensor is connected to RA0, which is a multiplexed operation. RA0 AN0 is a multiplexed operation. So, it gets it here. So, whenever this AD converter finishes converting one temperature value, so this the voltage value that is coming from the sensor into the digital value, it will send an interrupt to the microprocessor. So, the MPU unit, and when it is after getting that interrupt, so it will be it will be reading this 10-bit value of the AD converter into this processor. And then depending upon the temperature, we may like to turn on the heater or turn on the fan. If the temperature is above the setting the set value, then the fan should be turned on, and if it is below the set value, the heater should be turned on. So, that can be controlled by these two bits RA5 and RA6 of this port, and accordingly the bits D5 and D6 can be controlled by the microprocessor for port A. Port B and port C, so they are used for this LCD interface. In a port B, we send the pattern that we want to display, and this the other controls, the RS and read writes, these are the controls for the LCD. So, they are coming from this RC lines, this port C, RC1, RC2 and RC3 bits. So, they will be controlling the LCD panel. So, this way you can develop a very simple system using these PIC microcontrollers, or for that matter it can be any other microcontroller, but we can design embedded systems built around these microcontrollers and sensors. Okay. If so, the advantage is that ADC, timer and this LCD. So, ADC, timer and this digital IO. So, they are all part of the microcontroller that helps in the design of the system. Okay. So, after this we will look into another microcontroller, which is known as the AVR microcontroller. So, this is also quite common, and this is used very much in many of these processors, many of these embedded system designs, because of the same reason, because it is one of the powerful microcontrollers that we have. So, and again there is a range of such microcontrollers in the AVR series also, you can find a range of such microcontrollers. So, AVR, it stands for Advanced Virtual RISC. Okay. So, this is founders are Alf Egil Bogen and Vegard Vollen RISC. So, now they were actually two university students. So, when they were student at NTH, they started thinking about this architecture, and later on they developed the structure and refined it into developed the company Atmel Norway, and then the Atmel company was founded by these two chief architects. So, this is one of the success stories of the university projects going into the product. So, as far as the microcontroller is concerned, so it follows Harvard architecture again. So, this is program memory. So, there is the CPU. So, it is connected to, you can have program memory and data memory, and this program memory and data memory, they will have their individual buses, the program memory address bus and data bus, and data memory address bus and data bus. So, this width values 14-bit, 12-bit. So, they are varying, like if you look into different series of AVR microcontrollers, then these values will be varying, accordingly we can have different structures. Now, these AVR microcontrollers, they are a series of 8-bit RISC microcontrollers from Atmel. So, unlike ARM, which is a 32-bit RISC architecture, so this AVR is an 8-bit RISC architecture. So, this is so naturally the structure is going to be much simpler, like all the operations, if they are 8-bit operation, then naturally the hardware overhead will be less, and possibly it will be able to operate at a higher speed. So, they share the same instruction set as the basic CPU. So, all these AVR series of microcontrollers, they will be using the same set of instructions for the as we had in the basic AVR microcontroller, and they follow the Harvard architecture. 32 8-bit general purpose registers. So, it has 32 8-bit general purpose registers. So, that is a large number of registers you see. So, that makes it suitable for RISC architecture, and most instructions execute in a single clock cycle. So, which makes it faster among 8-bit microcontrollers. So, in a single clock cycle the entire instruction is executed. So, there will be pipelining and parallelization, whatever is there inside, but ultimately in a single clock cycle the entire instruction will be executed. So, architecture is very much optimized towards that. Mostly instructions execute in single clock cycle, which makes so that makes it better, and this is efficient execution of compiled C code. So, this is another very interesting thing, that these AVR designers, they did not expect the users to be very proficient in AVR assembly language programming. So, it was taken that okay, it is you can write your program in C code, and then there will be efficient compilers which will compile this C code into AVR code, and that philosophy is followed by many other companies, particularly if you look into say the digital signal processors. So, there also you will find that the programs are written in high level language only, and then through this efficient compilation, so they are translated into the machine language. So, it is no more like hand written programs. So, they are all automated programs generated from high level language. So, AVR is a family of 8-bit microcontrollers with large range of variants differing in size of the program memory, size of the EEPROM memory, number of IO pins, then number of on-chip features such as UART and the universal asynchronous receiver transmitter and the ADC. Smallest of this series is AT-Tiny 11. Okay, so that has got 1 kilo flash ROM, there is no RAM, and there are 6 IO pins. So, this is the simplest possible processor that we have, and the large one such as Atmega 128, it has got 128 kilo flash, 4 kilobyte of RAM, 53 IO pins, and lots of on chip features like ADC, UART and all that. So, there will be many such features that are on chip. So, we will try to see a broad overview of all these processors. So, if you look into say this 90S1200, it is a 20 pin chip with a flash of 1 kilo and EEPROM of 64 bytes, and there is no RAM. Then 90S2313, so it has got other features as EEPROM size is doubled and there is a 128 RAM locations are introduced. Coming to this Mega series, so Mega 603 or Mega 103, it has got 64 pins, it is a 64 pin chip, 128 kilo of flash space, 4096 bytes of EEPROM, so 4 kilo EEPROM, and then we have got 4 kilo of RAM space. So, that is one of the very advanced one. So, this way we can have a series of Atmega processors or this AVR processors, and their capacities will be varying depending upon the series that we use. So, we will look into some such representative microcontrollers. So, this discussion is for AT90S2313 series of microcontrollers. So, this is a microcontroller of AVR series. Okay. So, it is a high performance low power RISC architecture, it is a low voltage. So, the operating voltage can be 2.7 volt to 6 volt. So, this is another very good thing. So, you can have a wide range of supply voltage on which the processor will work. Maybe when you are operating at 2.7 volt, you do not get the same performance as when you operate at a 6 volt, but this power and performance, their trade off can be there, like you may want, you may be satisfied with a lower degree of performance, but the power consumption should be low. So, in that case you can operate it at a lower voltage, and the other side. So, you may want that performance should be good and I do not mind giving some more power. So, then you can operate at a higher voltage. The high performance CMOS 8-bit microcontroller. So, it is built on CMOS technology and it is based on the AVR RISC architecture. Since the microcontroller for AVR series, so it is also using the Harvard architecture. Okay, so, that is the same. So, features. So, it has got 2 kilobyte of in system programmable flash, where you can have this program memory. Then there is 28 byte of EEPROM. Okay, so, you can have some EEPROM where you can have only 28 bytes are there, but the essential values can be programmed there. Then we have got 128 bytes of SRAM, that is for the scratchpad purpose, 15 general purpose IO line, basically that IO ports, then 32 general purpose working registers. So, large number of registers. We have got timer counters with flexible timer counter with compare modes. So, we can compare the value of these timers and counters with some preset values. Then internal and external interrupts. The interrupts are there. Programmable serial universal asynchronous receiver transmitter, the UART. Then we have got one 8-bit timer counter. Then we can have one 16-bit timer counter. So, one 8-bit timer counter, one 16-bit timer counter. So, we have got analog comparator. So, this is another very important thing. So, many times we need to have two analog signals and we need to compare between them. So, in normal processing that we have seen so far. So, what we have to do is we have to take we have to convert those analog values into digital, and by means of some analog to digital converter, and then using that converter we have to run the program. So, we have to compare at the digital level. But if we can do it at the analog level itself, then this additional AD converters are not necessary. So, that is there. So, we can have this analog comparator in the AVR architecture. Then there is on chip oscillator and clock circuitries for clock generation. So, you have got on chip oscillator. So, if you so you do not need the crystals and all that. So, you can the oscillator will be able to generate the clock. So, we will be looking into this AVR architectures, particularly we will look into the registers, the instruction set, IO ports, memory and the CPU structure. So, registers, there are two types of registers, one category is called general purpose, other is called special purpose. So, general purpose register, there are 32 general purpose registers having storage capacity of 8 bits. So, named R0, R1 up to R31. So, these are 32 general purpose registers, and out of that register R0 to R15 and R16 to R31, they are different. So, they are as if they are two different banks and something like that. Can store both data and addresses, unlike other category where all the registers are not equally capable. Like in 8051 you see that we have got the registers, but for indirect addressing we can only use R0 and R1, or if you look into say 8085, then we have got this HL pair that can be used as memory pointer, but not all of them. So, you see that these general purpose registers in case of AVR architecture, so they can be all these registers can be used as data or address. And there are three special purpose registers: program counter, stack pointer and status register. So, these are the special purpose registers that we have in the AVR architecture. So, pointer register. So, there are three additional 16-bit register pairs, registers 26 to 31. So, they are called the pointer registers. So, so they are called X, Y and Z pointers. So, pointer X is this one. So, this is consisting of register number 26 and 27. So, they are this gives me the 16-bit address, and this is this is the X pointer. Similarly, we have got Y pointer, which is another 16-bit consisting of the registers register 28 and 29, and Z register consisting of the registers 30 and 31. So, read write from address X and they do not change the pointer. So, if you use this X pointer in your instruction, then it will be using this pair as the memory location address from where the value should be read. So, we have got 3 such registers x, y and z. So, if you have got pointer supported in high level language, so to convert it into assembly code, these pointer registers can be used. Then the status register. So, we have got a one status register sreg that has got 8 bit long flip flop, and each bit 8 bit long register, and each bit has got a different meaning. So, this I, the most significant bit is the I bit, which stands for global interrupt enable disable flag. Okay. So, it is that IE or that EI bit or IE bit for different processors, the global interrupt enable. Okay. So, that bit. Then the next bit is the T bit, which is the transfer bit used by BLD and BST instructions. So, these are 2 special instructions that we will see later. Then H is the half carry flag. So, half carry flag is basically that auxiliary carry sort of thing. So, whenever there is a carry generated at the middle, like if it is an 8 bit operation, so from the 4th bit, from 3rd bit to 4th bit, if there is a carry generated, then it will be this half carry bit will be set. Then there is S bit. So, this is for signed test instruction set. So, this is a sign bit. So, if the content is signed negative, then the S bit will be negative, will be 1, otherwise it will be 0. Then the V bit is the 2's complement overflow indicator. So, like when we are doing the operation, so there may be some overflow in the 2's complement notation representation. So, that way it is that overflow information. Then we have got the negative flag. So, this is so if the operation result is negative, then this bit will be set, then 0 flag and carry flag. So, they have got the standard meaning, this N, Z, C and V. So, they have got the normal meaning, but others they have got some special meanings. So, then we have got the stack pointer. So, it has got the concept of stack. So, in ARM we did not have stack by default. So, here we have. So, it is a 16 bit stack pointer. It holds address in the data space of area to save function call information. So, this is only holding the return addresses. Okay. So, they will be saved in the stack, and that is in the data space, that will be saved in the data memory. So, the register structure is like this. So, we have got this address 00 to 1F. So, we have got 32 such registers, R0 to R31, and out of that say this register number 26, 27, 28, 29, 30, 31. So, they are this XYZ pointers. Okay. As far as memory is concerned, so memory can be thought to be consisting of 2 parts, program memory and data memory. So, program memory is 1 kilo by 1 byte, and this data memory is 64. It consists of that 32 general purpose working registers, 64 input output registers, and then we have got the SRAM part, which is 128 locations of SRAM. So, that will be the data memory. So, program memory, flash memory. So, it has got 2 kilobytes of flash. There is then 128 bytes of in system programmable EEPROM program memory will be there. So, this is there, but this is used by the internal purpose. So, they are for interrupt function address 16 bit and double word opcode. So, this 128 bytes. So, they are used for this 128 byte that we have. So, they are used for interrupt function addresses, that is the vector table, basically that interrupt vector table. So, that is there. So, it is 16 bit and 16 bit and double word opcode. So, both 16 bit and 32 bit opcodes can be there, and the static data table. So, they can be there. So, this is another indicator, that is whether we are going for a 16 bit instruction or 32 bit instruction, that will be also contained in that EEPROM. And also we have to if there may be some static data table. So, they can also be a part of this in system programmable EEPROM. Okay. But actual program memory is the flash memory. So, that is the program that this microcontroller will run. So, that will be there in the flash memory. So, these are actually some for the 128 byte of EEPROM. So, these are for internal systems usage, and some static data tables can be put there. On the other hand, the data memory, so it is used for data, as naturally it is separate from program memory. So, we have got this Harvard architecture. So, program and data memories are separate. Then this 128 bytes of SRAM, so that is actually making this data memory. So, registers are reassigned the 32 bit address space, so 00 to 1F. So, that is 32 locations are those registers will be holding this a portion of the SRAM. So, 32 locations are reserved for the registers. Then the IO memory space, it will contain 64 addresses for the CPU peripheral functions. So, 64 locations are dedicated for these control registers, timer counter, AD converter, other IO functions. So, 64 locations are reserved for that, and this IO memory can be accessed directly or as data space locations, and the locations those of the registers like $20 to $5. So, you can either mention them as the register, or you can mention them as memory location. So, this IO memory part, so that is where you are accessing these timers, AD converters and other IO routines, other IO modules. So, that can be accessed both way, and stack is effectively allocated in general data SRAM, and the stack size is limited by the size of the SRAM. So, SRAM size is, it is 128 bytes. So, out of that 32 bytes are gone for the registers, 64 bytes are gone for the IO memory space. So, total 96 bytes are spent for this by the system. So, you are left with only 32 bytes for the stack. Okay. So, this so in this, so if it is SRAM is limited to 128 bytes. So, you can initialize this your stack pointer to location 97, and from that point onward your stack will start, and it can go up to 128 only. So, the AVR instruction set, so it has got 118 powerful instructions, and most of the instructions, they are single cycle execution instruction. All arithmetic operations are done on registers R0 to R31, and mostly instructions take on one cycle for execution. So, as we have already said that it will be all arithmetic operations are done on registers. So, R0, so you cannot have, so R0 to R31. So, in some sense you can say okay, they are memory locations as well, because R0 to R31 is in the data RAM. So, that way it is fine, but it is the operands are register operands. Okay. So, also this is similar to other processors that we have seen, where this, for example, in ARM processor we have said that all the operations are having registers are operand. So, here also the same philosophy is followed, but of course, you can say that okay, this is a RAM is also part of the processor. So, register and memory does not have any difference.